Welcome to the class of Lie groups and Lie algebras. And then when I first got the topic, immediately I decided that's not going to happen. So let's just put it in a nutshell. And of course, I checked the library, and I realized our favorite author, Tony Z, already had a book called Group Theory in a Nutshell for physicists. So since whatever I'm talking about will be way smaller than what he's talking about, so it's the world's smallest nutshell. Okay, and group theory has so many topics that I don't have time to embrace them all by myself. I can certainly tell you a lot about it by talking really, really fast. But if you know me well enough, you know that I don't talk that fast. So I have selected a series of self-consistent topics, and it will be listed as follows in the outline. And we'll go with the second strategy. If I run out of time, I'll try the first one. Okay, so the first class, as I have mentioned, we'll try to just have fun with finite group. It's a great place to start for some reasons. One of the reasons is that it introduces a lot of concepts, and I have some gadgets that we can look. That has the visual groups theory by Nathan Carter. Today's lecture would be almost entirely based on this cute book. It's a mathematics book, has over 200 figures, and has 292 pages, including index and references. So basically, you open the page, you expect to see at least one picture. So I love that book, and that's what we're going to talk about today. Not all 300 pages of them. Okay, visualize finite groups. We'll come back to this. And then, tomorrow, we'll do the introduction to Lie groups. It's just what is Lie groups and what kind of Lie groups we're interested in. Well, for me, I guess you haven't known, but you will gradually know Dan, my husband, will teach you QFT1, QFT2, QFT3, and maybe QFT ... And basically, I'm going to teach everything he dictated me to teach you. Otherwise, he will have issues with me, which I want to avoid. Okay, so we'll talk about what are they and what kind of Lie groups we're interested in, And the next lecture will be on structure constant. If you have heard of them, all you can guess, since this is one of the names that are not misnamed, it actually describes the structure of the group. So it basically says, if you want to study a Lie group, we'll be physicists and do linear approximation. So we'll only study the Lie algebras. And if we want to study Lie algebras, as long as we know the structure constants, that's all we need. So it seems to be an important thing to talk about. And then the next lecture will be everything literally about SU2. And we'll learn that SU2 plays a very important role in our life. And if we can't do it all in the lecture, we'll certainly finish everything about SU2 in the tutorial. And actually, tutorial has a question one part, I don't know, E, F, G, that says, find all the irreducible representation of SU2. So, and then we'll say, well, with, I don't know, mathematician, physicist, you say SU2, you can just keep going, right? So next class, we'll talk about SUN. And then we introduce something fun called a Young tableau. And then in the same class, we'll mention this very good representation called adjoint representation. At the moment, you can just say it's good because it exists for all the Lie groups. Say for all the Lie groups, you can at least have one non-trivial representation. That sounds nice. And the last lecture, well, I really want to get everything done. So last lecture, let's say some miracle happens. We'll talk about the miracle later, presumably last lecture. And then the notebook goal is we're going to classify all the Lie algebra. Just like the botanics people. So that's how things I wanted to go. And if it takes any other routes because you stop me and ask questions, all the better. Okay. So I guess now we come back to the first lecture. Visualize finite groups. Or in my own words, how I stopped varying and started loving group theory. Okay. So group theory is a theory about symmetries. So we can take a mandarin orange as example. Dan says this is a national fruit of China because it's a mandarin orange. Anyway, see this orange has a head, and if you hold this orange like this, and you can just rotate it. If it's a really fresh orange, this one is outdated, but then you can rotate it, and you see this orange more or less remain the same. So I claim this orange has a U1 symmetry because I can rotate any angle, and this angle is a continuous parameter, which will delay to next class. But when you see an orange, I can't help but peel it. Okay, let's peel this orange. And we'll get to today's topic after I finish peeling this orange. So if you look at this orange, mandarin oranges, they're easy to peel, and they have sections. This particular one has 11. Because of these section lines, now you can't really rotate it by arbitrary angle. You have to rotate it by 360 divided by 11. It's not divisible. Last time it was 10. But anyway, then you can only do, so you get the point. I can only rotate it very discretely. So I have broken a continuous symmetry to a discrete symmetry or a finite group. And in this particular case, it's a C11, which will come back later. It's a cyclic group with 11 elements. After rotating 11 times, then I come back to the original orange. Okay, so of course, after I see a peeling orange, I'm very tempted to eat it. I really love mandarin oranges. And if I eat it, it becomes something completely different. That we don't talk about it. Okay. So, but suppose, let's assume I did eat the orange and gain some energy. And then we want to play some game. So there is this world's famous toy, and it's a really huge version of it. So this is a Rubik's Cube. In China, we call it a magic cube for some reason. Rubik's Cube is a toy that has very simple instructions. It says it has 6 faces, and you can just take a face and rotate it by a quarter, or 90 degrees. Or you can take the face, okay, the big cube is very visible, but it's very hard to turn. And turn the other direction for a quarter. And you can do it to all the 6 faces. And the goal is that somebody scramble, your friend or your rival, scramble a Rubik's Cube and give it back to you. And you are able to get it back to the configuration that each face is at the same color. Okay, so the claim is that this Rubik's Cube forms all these moves you can possibly perform, all the moves including the very complicated move, take this face a quarter, the other face a quarter, the other face a half, dali dali dala. You take all possible moves you can do to the Rubik's Cube without destroying it. They form a group. And they actually have a name. It's called the Rubik's Cube group. So let's see. So it's probably a great idea here to introduce what is a group really. Okay, so the formal definition of a group is that it is set G binary operator. You might have heard the word multiplication, but let's just say it's a binary operator. It's denoted by a circle. Okay, so in this case, we have a set of moves. All these moves is an element of the set. And the binary operator just says, you take two moves and you perform them in sequence. That's a binary operator, and you have a complicated move we call a new move, which is also in the set. So, of course, you can't just say, let's take a set and define binary operator and that's a group. It has to have some special property, and the first one, you say it's closed. So if we have element A, B belongs to G, we require A operated with B also belongs to G. So this is easily demonstrated on this cube. You can turn it some way and turn it some way, and it still is a combined move that leaves the cube, still remains a cube. Okay? There's no moves you can combine together and somehow this cube turn into an orange or some other shape. Okay. The next property is associative. This you must be really familiar with. Says if I have three elements, then I can add parentheses as I wish. So this is really like multiplication or addition in that sense. And for this Rubik's Cube, it says you can combine the first two moves together, call it a new big move. And then you perform another move on it. It will be the same as you combine the second two moves into a big move and perform this way. After all, you are performing these three moves in sequence. Okay? And then the third property is that there exists an identity, normally denoted by E, and says identity act on the left, on the right will be the same, and you get the same group element. It says that identity in the case of playing a Rubik's Cube means I'm doing nothing. So if you do nothing and then do something, or do something and do nothing, this is equals to do that something. Okay, and this is very carefully written that to indicate that this binary operator might not be commutative. Okay, we'll get to that. That's why I don't like to call it a multiplication. Okay, the next is for any A, I can find A inverse such that A inverse is the inverse of A that gives me identity, which is also easily demonstrated on this cube. If you turn it one way, you can always turn the other way, and it equals to nothing. Okay, so here we know what is a group. The group is a set with a binary operator that is closed associative. We can find an identity, and the inverse always exists. Okay? So now, of course, I'll spend the rest of the lecture teaching you how to solve Rubik's Cube, which I don't know how to solve it. But say, suppose I want to solve a Rubik's Cube. What kind of options do I have? Let's say, one, take a random walk. I just keep random doing things. And hopefully, it will somehow return to the original configuration. I have tried that strategy. Didn't work as well. So I try my second strategy. Whenever I'm asked to do anything, I say, Google, how to solve a Rubik's Cube. Yeah, you get tons of tutorials I can follow. I try to remember, but not much. But yeah, you can follow this algorithm, and you says if it's this configuration, perform these moves in sequence, you will reach that configuration. You solve the first layer, second layer, and then half of a third layer, the other half. Okay, but now this is see my vision, this is not very optimal. If you Google Rubik's Cube, there are people, I think it's a computer scientists, they actually write things as solve any Rubik's Cube, and there is a gold number. The gold number is 26. If you restrict the moves to limit it to taking a surface, tweak a quarter, it says no matter how hard you try to scramble this cube, it will take at most 26 steps to get to the original configuration. And now I become very ambitious. See, the random walk is taking me close to infinity number of steps. And those algorithms that I tried, it's definitely not 26. It's probably 100-ish. So I really want to get this optimal configuration. Now what do? I envision I have this big book. Suppose I have a really, really huge book. And each book, I have a configuration. Any configuration of this cube is recorded in this book. And I can just open this book, and this book says, take the front face, turn a quarter, you will reach configuration page 11,345. Then I go to that one. So it will be listing if I do this move, it will take me to that configuration, and congratulations, you are one move closer to your solution. If you take the opposite move, you'll be one move away from it. Okay, so I can just open this book. So whenever somebody hands me a cube, I can just look it up in this book, and then follow the direction to take one step closer, and eventually I get it back. And that book will give me the optimal solution of 26 moves. Okay, so I really want to get this book. And I realized it's quite impossible. I was informed this book would be of 40 billion pages. So actually this number makes me very dizzy. I've played the game for a whole day. So I'm going to fall asleep on the mattress. So if you stay in PI for a little longer, you might have heard the saying, or you actually might have your own experience of the saying, that sleep is for the weak. But for the people who are very fancy and rich, that enjoy the luxuries of sleeping, which I encourage you to do when you have time, they are worried about a different problem, such that it's called a mattress problem. So they have a fancy mattress. So suppose a person that sleeps regularly on this mattress at a very, say, regular configuration, then they will input a dent on the mattress. And then that will damage the mattress eventually. And if it's a very fancy mattress, it will want to circulate this mattress in all configuration, such that they will, say, just like do things like this, such that all parts of the mattress get equally dented and can even out, so that they can prolong the life of this very fancy mattress. So then I was like, this is a great problem. As I'm a theoretical physicist, I'll say, let's suppose the mattress is spherical and in a vacuum. But actually, this mattress problem is much easier than the spherical problem, which we will solve in the fourth lecture about SU2. Okay, so let's just take the mattress problem as it is and try to solve this. So for this mattress problem, I can actually build that big book. Actually, it's a really small book. It takes less than a page. So, but let's have some notation clarified. My hand is the headboard of the bed, and this is the mattress. So I can call this configuration mattress by the letter that is close to my hand. So this is mattress configuration A. You can start with anything. I'll start with A, and I'll say at this location, identity is doing nothing, so I will be remaining in status A. So it's going to be harder for me to label each move by the sequential move. It's just going to be long. So it's just a bookkeeping that I'm going to use the configuration of the mattress to denote the moves that are going to take it to it. It's just easy to write letter A, B, C, D instead of the moves that I'm going to take to get to D. Okay. So if given a mattress, if I start at a configuration A, I could do a horizontal flip of the mattress. I'll reach status C. So in my big book of 1 page, I can do a horizontal flip and I reach configuration C. And I can also do a vertical flip, and that will take me to configuration B. And then I can do another horizontal flip and take me to configuration D. And of course, it assumes I know the result. If I take another vertical flip, I get back to A. Okay, so that's my big book. I reach all the configuration I want using the basic move, horizontal move, and the vertical move to do it. Okay? So that's the book. And this book is very useful to study finite groups. And it's realized by mathematician Cayley. Not sure if he starts within the mattress or not. But these things are called the Cayley diagram. But since we're mathematicians, we're not going to have such detailed graph. We're just going to erase all the configuration. Since we're talking about group theory, everything is symmetrical anyway. So it doesn't matter where we started. We're going to be experience all the nodes and discover them all. And in the process, we come up with some lines. Let's color them. It's not the best color. To make sure that we know that they are different moves. Okay, so this is actually the Cayley diagram. And using this Cayley diagram, we can study useful things. But let's summarize how to draw a Cayley diagram. Which will draw some others. So it's nice to have a recipe for everything. Okay, so first, find the generators. The generators are the basic moves you believe that will span to the entire group. Suppose I have basic moves, vertical flip and a horizontal flip. It will lead me to all the configurations of the mattress. So those are called generators. Okay? It doesn't have to be optimal. It can be over-complete. You can have a redundant number of generators. We'll get back to why do you want to be redundant. Okay. And next step, pick your favorite starting point. They are all equal. But to start drawing a diagram, you have to pick one that is more equal than the others. But nobody cares because they are all equal. But let's pick one. And explore with the generators you choose. So for example, I chose A. And I explore with the horizontal flip and the vertical flip. And I found the nodes C and D. And probably find a new nodes. Okay. And then pick a new node and explore. I guess we should say, if you, I'm sure all of you know some sort of programming, but basically this part is like, do this while there is a new node that hasn't been explored. So you just keep doing it. So I discovered the C or D, and I immediately use my generators again. I discovered B, and I want to apply this exploring generators thing to each node to make sure I'm not missing anything. And then eventually you reach a Cayley diagram. You erase your nodes and then make it pretty. Wasn't that pretty, but we make it abstract. Okay, so that's how we draw a Cayley diagram. And the reason we want to draw a Cayley diagram, or an abstract Cayley diagram, is because, let's give it a name. I normally just call it a matrix group, but there are official names. It's probably discovered by somebody called Klein, some famous mathematician Klein. So it's called a Klein 4 group because there are 4 nodes. And sometimes you also say V4, and V stands for the German word "viel," which means 4. Okay. So this group can describe other configurations. Instead of flipping matrices, suppose you have configuration 2 light switches, and your basic move is turn on the first light or turn on the second light. And you can see there are 4 light switch configurations, and they are also related to this Cayley diagram. And there is another story about the renowned physicist Richard Feynman. Now he has many stories. And he was rejected to army by a psychiatrist. And as the rumors on the internet go, the reason he is rejected by a psychiatrist, because during the psychiatrist visit, the psychiatrist says, "Put your hands out." And so Richard Feynman says, "Okay." So there's 1 palm up and 1 palm down. And the psychiatrist look slightly confused for some reason and says, no, the other way. Richard says, "Oh, okay, the other way." So instead of this vertical flip or horizontal flip, what Richard Feynman did is the combined move. And in the matrix sense, that the combined move of a vertical flip and a vertical flip and a horizontal flip, as you can see, is called rotating the matrix. So there is another move that combines them. So we could have this move too. As I said, it doesn't matter. We don't need it to find all the group members, but it's just the third generator means rotating this matrix. And you could also try to draw another one that, let me try. This would make all the moves look equal. Because they are. They are all generators. I don't discriminate over them. So this is also a valid Cayley diagram and describe exactly the same group, the matrix group. And you're like, why bother? When I have the chance to choose 2 generators and get this diagram without the dotted line, why would I go for that one? Well, that's pretty. But we'll come back to that. So, well, before I move on, I should actually solve the problem I propose, that how exactly you want to flip your matrices. The place you rent now might not be worth the trouble. But the golden rule from the mattress company, who sell these fancy mattresses, says you want to spin in the spring and flip in the fall. Because if you have a real mattress, the vertical flip is slightly more challenging than necessary. Okay, so this concludes the introduction of the finite group. And we're going to dig a little more by understanding the 5 families of the finite group. There are many more than that, but we should start somewhere. first family we already encountered. It's the cyclic group. I guess I could also call it the orange group. Cyclic groups is normally demonstrated by a propeller. So if you don't have fancy AC conditioning, you might have a fan. And those fans have the property, if you rotate it by, if you have 3 leaves, if you rotate it by 120 degrees, it will be still the same fan. So this is this propeller group denoted by Cn. And so let's try to draw the Cayley diagram for it. You start with one node, and then you just keep rotating, keep rotating, keep rotating, and dot, 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 keep rotating, and you get back. So, we're done with the first family. We have drawn the Cayley diagram, which it's known as the big book. So definitely encode all the information you ever wanted about the group. So those are the cyclic groups, and all the Cayley diagrams look like a bracelet, and then has random number of nodes depending on how large your cyclic groups. And we have encountered C11 as an orange. And if you have an octopus, probably can get a C8. And shall we move on? Well, let's try dig a little deeper. I would like to pay special attention to C6 for some reason, hopefully will be quickly reviewed. So let's draw the C6. And it will form a hexagon if I draw it evenly. So this is that Cayley diagram for all cyclic groups specialized to C6. And we could even be a little bit mathematical about it. And let's say this is A to the 6 equals E. Well, I probably should say this is A to the N equals E. So if I start with identity and act with A squared, and you just keep pushing, and eventually I get it back to E. Okay. The cute thing about the number 6. So right, throughout the lectures, you will learn some fun facts about arithmetic. Fun fact about 6 is that it's divisible by 2. So suppose I'm silly. So just let's assume I'm silly. And okay, maybe not a good assumption, but that instead of A, I decide to pick A squared as my generator. Why not? So this will be the route I'm taking. It will take me to A squared, and then take me to A fourth, and then take me back. It's a silly way to do things. As you see, we didn't explore all the group members. Okay, but I have other things to do. I could choose A as my generator, but then I get back to that configuration. I'm trying to be adventurous. So I decide to take A cube as my next generator and obtain A cube. Now I reach a new node. Since I have a new node, I'm always allowed to use my other generator, such as A2, to start exploring, and hence discover A5 and A. So this, well, since I have a new generator, I should have a look at some other nodes and apply the new generator. And hence, I obtain a new Cayley diagram, which is symmetrical. That's good, because we're studying groups. If your Cayley diagram doesn't look symmetrical, it's probably not a valid Cayley diagram. So this follows the rules of Cayley diagram. I decided to choose A squared and A cube as my generators, and here is the diagram I generated. And here we observe observe something interesting. From C6, well, it's a hexagon. What else can I say about it? But from this one, very interesting things going on. For example, I have E and A3. And if you look at this long enough, this is C2. C2 is something go there and come back. So, I discover familiar diagram in the new diagram. That's interesting. And then, of course, you can look at again, and you discover a triangle from it. So that's E A squared A first, and this is C3. So, the reason sometimes you want to be redundant with generators is that you could discover things you have already discovered, hence use the knowledge of the past. So, what this tells us for Cayley diagram is that if you identify some parts of the diagram, like this little part, or this triangle, as something you have seen before, this is an indication that our group has structures, which is the subgroups. So we claim that C2 is a subgroup of C6, and C3 is also a subgroup of C6. And why not? We can also have the official definition of a subgroup, which is not that crazy. It says subgroup, it says A, big A, is a subset of G with the same binary operator, and it's also a group. So if it's a group and it's a subset, then it's a subgroup. Not that complicated. In particular, you want to include the identity, because as long as you're a group, you want the identity. But that's it. So if you draw a Cayley diagram, sometimes you identify subgroups this way. And we can also, and here is also a good point, it says, suppose I have C2 and C3. How can I get a C6? If I have all the subcomponent, can I just build it up and get a C6? It's like a Lego. Yes, we can. And this operation is called the direct product. And in Cayley diagram, this is relatively simple. So suppose I'm interested in C2 times C3. It says, draw a giant Cayley diagram. Okay. This is my giant bloated up C2. Still look like C2, it just has giant nodes. And the reason it has giant nodes is I'm going to draw a C3 in it. And then, I'm sorry, I'm going to cheat because I have eraser. I'm going to erase the giant node. You're like, no, these are two C3s. Well, I'm going to link the corresponding node with that C2 generator. So this will be C2 more direct product C3. And if you look at this diagram, and you flip the one of the triangle and elongate it, these two diagrams actually look the same. Or I can also redraw this C6. It doesn't have to be in 3D. I could just squash it down and make this triangle bigger and squash it down. So I could draw it this way. configuration of C6, and which illustrate more that C6 is equals to C2 direct product C3. Okay, so, and a fun fact, if you have CMN, when MN are co-prime, and you can prove that this is always true. Okay. Now we're done with cyclic groups. Okay. And we might come back to them later for some useful purposes. All right. So next family. And while I'm reading words, I have a very silly question to ask. You might have heard about it. So the question is, what is purple and a commute? I guess you haven't heard it. It's an abelian grape. So the next family is the abelian group. Okay. So abelian means commute. So it means that remember when we talk about the group multiplication, that the group binary operator, we emphasize it's, I don't want to call it a multiplication because A, B might not equals to B, A. It's not necessarily true. And the abelian group is just the group with this property. Says if the binary operator actually commutes, then this group is abelian. And what do we want to say about abelian group? Well, not really, because we have a fundamental theory of the finite group says any abelian group can be written as a direct product of maybe gazillion of them, but cyclic groups. So all abelian group is same, holomorphic to some direct product of many cyclic groups. Since we have already nailed all the cyclic groups by drawing all the Cayley diagonal there, and we have learned all the direct product, how to do direct product, then I guess we're done with abelian group. Carry on. The third family is called the dihydral. Oh gosh, group. And then it's denoted as Dn. And it's also known as the group for polygons. Okay. Well, so it's mostly the symmetry of the polygons if for most n's, but let's be systematic about it. So it basically, the basic generators or operators for dihydral group is rotate by 360 divided by n degrees, or flip. So there are two kinds of operators. If you have a polygon, you can rotate, and you can also flip. It's like a mirror symmetry. But I like to be very systematic about things. So let's start with n equals 1. So then, by the limitation of my English, as you might realize, I might not be a native speaker, that I decide to name It's a point, really. But I want to be very systematic. So I want to name this thing unigon because it has n equals 1. And then I was being very silly, so I looked it up on Google. Then you realize unigon actually is a word, means a mystical creature that is a hybrid between unicorn and dragon, and hence very powerful.
Unicorn, man. Don't mess with.
Don't mess with unigon. But nevertheless, because the point is very powerful, that's why we stuck with point mass for a long time. Anyway, this unigon that rotated by 360 degrees. Okay, that's not doing anything. That's called identity. But you can flip. So we derive the formula d1 equals c2. And we can move on. N equals 2. And this is a basic line. But you know, I like to name things, as you will gradually know me. So I will call it a bygone. And it's a line. But Dan says, just let the bygones be bygones. I have no idea what he means. But then I look it up. Apparently, it means let the past pass. Okay, so this thing, it will have rotated by 180 degrees, which means that's a C2. And the flip is another C2. So we know D2 is C2, direct product C2. And if you think about this having two big nodes and put a C2 in each, this process will give you back the matrix group. It comes back here, the Klein 4 group. All right, for n equals 3, finally we reach the polygon. And this time we have a triangle, or equilateral triangle. And for this, it's slightly more complicated, so we'll move to a new board. And also we'll actually try to do it. Let me think. Yeah, that will work. All right. Oh, come on. That'll become a fixed board today randomly. And I have a triangle.
Oh.
Well, you can also just draw a triangle on your paper, on your pad and rotate it, but I have to hold it up. So it's just, this is just my notation so I can remember where I am. So I denote a triangle by the top of it, and I guess counterclockwise. So I call it this triangle 1, 2, 3. And I'll call this my starting point. But as I said, all configurations are equal. So you can pick anything. So let me start this and follow the operation rotated by 120 degrees. So let me rotate this. I guess I'm rotating clockwise. Clockwise. And I reach configuration 2, 3, 1. So that would be my new configuration. And I keep doing rotating clockwise. And then I get 3, 1, 2. And if I rotate it again, I get it back to myself. And then I have another generator says flip. Ta-da! And I reach 1, 3, 2. And then I can keep doing my rotation thing. Then I reach 3, 2, 1. And then I can rotate again. And I get 2, 1, 3. And then rotate it back to myself. And let me check. I can do that. So I have 3, 2, 1. Then I flip. I get a 3, 1, 2. All right. And that's the missing link. Okay. So this is our D3. The symmetry group of an equilateral triangle. Yes?
So it seems like all the cyclic groups would also be abelian, right?
Yeah.
And if you define that the abelian groups can also be a sum of cyclic groups, then
Direct product.
Direct product. Sorry. Then all the abelian groups would also be cyclic groups.
No, because
it's not cyclic.
Cyclic means that. So for example, C2 direct product C2 will give you V4. It introduces a new generator. In the case of C2 and the C3, you say there. So basically,
you have the Cmn equals Cm.
Multiply Cn. That is, sorry, I should write the condition down. I was mumbling and didn't write it down. Sorry. Mn is coprime.
Okay.
Sorry. Yeah. So basically, in particular, C4 does not equals to C2 direct product.
Okay.
Very good. That clarifies things. And that's actually very important. We'll come back to that point again. Nevertheless, we finished this triangle diagram, symmetry of the triangle, which looks like this. Does it look familiar? Yeah. I was like, huh, it's right up there. And are they the same?
No.
No. Because?
Well, that one is not commutable.
No, that one is not commutative. Very good. Let's try to see that exactly that point. What do you mean by that one is not commutative? Well, by definition, all cyclic groups are commutative, but let's just put it down and take a look at it again. It says, if I do this rotation operation and then do some other operation, I reach this guy, but I can also do this line right. That's why I should have color everything. So if I do the green line operation followed by the white line operation, I reach to the same node. So it says white, then green, we get this node, and then green, then white, we get the same node. So that one is commutative because it's a cyclic group, it better be. But this one, if I go with green and the white, I reach this guy. But if I go with white and then green, I reach some other guy, which is indeed not commutative. This is a very interesting observation. This is the first non-abelian group that we encountered, which is D3. It's non-abelian. And you can see that the arrows indicating from which node which node has been reversed inside, which caused the non-commutativeness. All right. But we already said this. If I can see something familiar, such as this, or such as this, we call them subgroup. Correct. We still call them subgroups. So D3, again, has subgroups C2 and C3. You're like, fun question. Give you C2 and C3, how do you get it back to D3 then? We already used the direct product. So to answer that question, we need quite a few new definitions. It involves something called a normal subgroup. But, okay, so all elements are equal. None of them are really special. If you look at the configuration, in the Cayley diagram, all the nodes are equal. You can call any one of them identity, and then you can just follow the generators and generate the rest. But all subgroups are not equal. Some subgroups are more special than the others, and they're called the normal subgroup, and which is very interesting because they are not normally found. They're actually rare. Nevertheless, the mathematicians call them a normal subgroup or invariant subgroup. But before that, we have to yet introduce, to determine if a subgroup can be promoted to normal or not, we need another definition, which is interestingly related to the musical, very popular recently, well, past few years, called Les Miserables. Because Les Miserables is a story of cosets. So let's introduce the definition of coset. Coset is, let's say I have a subgroup. Okay, I'm going to redraw this guy because this 1, 2, 3 thing is very hard to write. So D3 has an algebraic definition, says A3 equals identity B squared. Okay, let's use rotation to the cube equals identity and the flip to the square equals identity. And that's not good enough to get D3. You have to specify that they don't commute. Instead, R followed by F will give you F followed by R squared. So that's just bookkeeping that I'm going to just draw D3 over here. Okay. Purely good bookkeeping. So I'll start with identity, and then get R squared, come back to myself, I flip, and get R. Get a flip R, and get a flip R squared, and then come back to this guy, and then link the other two. Okay. Otherwise, my cosets might be too long for me to write down. Okay. So now, let's take our subgroup E and F, which is the C2, to get the cosets, you just multiply all the group element to this subgroup. And of course, we'll have a lot of redundant. For example, so let's multiply by identity. That's quite silly. It gave me the same. So this is my coset number 1, which is this subgroup. This is one coset. And I could also multiply by CF, which gave me still the same. So you could, what I do is take a subgroup and then multiply by all the group elements. There are 6 of them. Yeah.
Isn't it like kind of confusing to label the states on that diagram with like E, S, whatever? Why not? Like, why wouldn't we label the lines with F and R?
It's the same thing.
It's not the same thing though, because you can go. You could call that R there. You could call it F R squared F, and it would. You know what I mean? It's just
this one.
It's changed it.
F R squared.
See that?
F.
See R?
Yeah.
You could equivalently call it like F R squared F, right?
Yep.
So isn't it like? Doesn't it make more sense to label the lines as the elements in the group, like R and F?
Right. So what you propose, let's draw a smaller version of it, would be R, F, F,
Yeah.
F. right? That'll be a nice diagram. But then this way of labeling, although you're completely right, some of them will have multiple names. I can just keep multiply something like this and have lots of names. But for this configuration, what I can do is actually write down all the elements in a group. So I can say this give me these three, although each of them is like an equivalent class, has many names. But in this labeling will enable me to write down all the elements in a group this way. And this labeling doesn't really let me do that.
Okay.
So, yeah, indeed. So these are really an equivalent class. It's anything will, starting from an identity, any operation could be a really, really long sequence operation that reach this node will give you different names. But then you just say, well, they're all equivalent.
Mm-hmm.
Because if you look at this triangle, it indeed only has 6 configurations. You could label one particular configuration by different names, but if you have a triangle in hand, you would know, oh, they look the same. So they must be the same name.
Yeah.
Okay. Question?
Why did you change from operation to multiplication now for this example?
Oh, no. You are completely right. That's just because I'm silly.
You can call it composition. And why do you call it FR and not RF, R composed with F?
Yeah, that's what I'm looking at.
So,
Thank you.
No, it should be R composed with F. Because F goes first.
F comes first, yeah.
Oh, so you want to use F?
I mean, call it whatever you want.
Right. So I'm just listing the operation I do in sequence, and you are saying it's more like there is something and an operator acting on it and the operator acting on it.
It doesn't matter, right?
It's just
what I would do. But
yeah, you can do whatever you want as long as you're consistent. And yours is more familiar to people who are doing applying operators a lot, and that's how it goes. And I'm just really listing. So
just to be clear.
Yeah, thank you. It's very important. What Dan is very favorite of being technically correct. He says technically correct is the best kind of correct, which you will find it out from this functions, etc. lecture. Anyway, yes, very good. So it's just my way of labeling. I'm just listing all the operations. This is the first operation I do, this is the second operation I do, and blah, blah. And then your way is more like say F acting on some X and blah, blah. All right. Okay. Right. This is very important that what I meant is from each member of the subgroup, I decided to perform another operation of E, which didn't lead me to anything new. And from each member of this coset, the subgroup, I still didn't lead to anything new because it's a set, it doesn't have order. But when I act onto it with R, indeed, I get something new. Or if I act on with R square, indeed, I get something new. Oh, all right, that would work. And of course, there's other members such as FR and FR square. So, well, I already did 4. I might as well do all of them. So, acting FR will give you FR and R because F square equals 1. And then the last one will give me FR square, R squared. But what I realize is they are redundancy. And let me just circle the ones that are not redundant, which includes the original one and this two. So for this graph, that graph is going to look so pretty that I can't even lay my eyes on soon. So that are great. And then this guy. And this guy. All right. Okay. So this is called, those three things that are in orange circle are called the right cosets. Because it has the elements on the right. Okay. Well, as Thomas pointed out, that we should be very careful about the multiplication and the binary operator. And hence, I can do the same thing, but with the element on the left. So there is, of course, something is called the left cosets. And we still start with E and F, and if you work it out, that will give you this. And as Alan pointed out, there's a lot of redundancy naming here. Our F can be also named with FR square. Our square F can be also named with FR. Which means that I'm in great trouble of drawing more orange circle on that thing. So I'm going to use this and imagine that they are labeled correctly. So the left coset would give you these guys. And as you can realize, the orange circles and the blue circles are not the same. And that's why, after investigation, we claim that the C2 is not normal. It's only one when we find out the left cosets and the right cosets are the same. Then we call them a normal subgroup. And if we do this exercise with the C6 up there, you would realize indeed that the C2 would be a normal subgroup because it's abelian. So you would only get this kind of coset configurations, and you will never get out. Okay, so now we figure out C2 is not a normal subgroup, and you can continue to do this exercise and realize C3 is a normal subgroup. And when it is a normal subgroup, we can introduce a new operation called quotient. Quotient says I can divide the original group by the normal subgroup, and then this is the quotient, and it's called the group of the cosets. So for this particular example, we have D3 divided by C3 equals C2. And this is actually this quotient operation. It's easily demonstrated by the Cayley diagram. It's the opposite of direct product. You identify some cosets. If they are the same, then you can just collapse them. So we can't use this diagram per se because the cosets are not the same. But if we have done it for C3, it will just be the outside triangle is a coset, the inside triangle is a coset, and you collapse them down, you get the C2. So it's like there is a big triangle, there is a small triangle, then you put it back to two giant nodes, and then collapse them into two nodes, and link it by a operation, give you C2. And you can't do it the other way. So you do have this equation But this is not valid because C2 is not normal. And now we can finally answer the question, how do we get a D3 from C2 and C3? And that is called the semi-direct product. And the semi-direct product says that there is a normal subgroup, and I will call the other one, C2, as a overall structure. And if I have the overall structure, again, I draw giant nodes. And then again, I draw these three in them. But since it's a semi-direct product, I'll change the angle direction. And hence, it's called a rewiring in Cayley diagram. You take the wires out and come back again. So you put two C3s, but different, into the two giant node, and again, you erase the giant node, and then link the corresponding nodes. And as you can see, if I squash this diagram down, we'll give it back to D3. Okay, there are some complicated mathematical definition we would get to. Some involve some alphamorphism, automorphism. Anyways, I said it once and I said it wrong, so we'll just check it on the notes. But this is how you do it in a Cayley diagram. You blow up the overall configuration nodes, and then you draw the normal subgroup as many times as needed, but do some rewiring. And that will give you back D3.
Go on.
Yes?
Could you repeat me why at the end C2 is not a normal subgroup?
It's because the left coset,
Yeah.
which is the blue ones, is different from the orange cosets, which is the right ones.
Ah, okay. So if we did it with C3, we will get the same connection like circles?
Right, because we can just do it for C3. It's not hard. You get E, R squared, R squared.
Yeah.
And then you get F, R squared. And the other one, you get the F, R square F, but these two are equal, that's two equal. So then, you know, this is the left coset, and this one, the third one is the right cosets, but they are the same, because they are same in the set sense. The order in the set doesn't matter. So yes, so if you did it for C3, you'd realize, the left cosets equals to the right cosets, and hence it's normal. And if it's normal, we can divide. And if you want to do a semi-direct product, you have to know which subgroup is normal, and normal is the one that you want to change the arrow direction and such and such. Okay, yeah.
I think you have this symbol for the semi-direct product the other way around. Like you want.
It's possible. I can't remember which one. Don't trust me on that. I'll check.
The triangle part should point towards the normal subgroup. That's
will be.
But
C3 is the normal one.
Yeah, exactly.
Points.
So that's right.
Points.
Yeah.
Oh, okay. The triangle points to the normal subgroup. Huh. That seems to be easy to remember. I'll try to remember. Okay, so and you're like going out of time, and you have two more family of groups. I'll try to talk as fast as possible. So for the first family, it's called the permutation group, and we already see one. Look, this is the permutation of three numbers. So we know that S3, it's also called the symmetry group theory for some reason. So S3 is basically D3. And for beyond that, we'll leave it as an interesting exercise. There's also a Cayley theorem says that every single finite group is a subgroup of some sort of permutation group. It tells you if you understand all the permutation group, you basically understand all the finite groups. So it's a really, really, really complicated subject. And the last group is called the alternating group. Alternating group says, well, the symmetry group is so complicated. Let's understand half of it. So it basically says, take all the permutation and square them. And then you will get some other things. You collect them. It happens to be half of what you have before, and you call it the alternating group. And for example, this tetrahedron, and if you happily do the same exercise as we did for the triangle, it's slightly tedious and long. So the basic move is good that it's made of a foam and doesn't destroy it. The basic move is fix the tip and rotate. Or you can take two opposite ends, the midpoint, and you can flip by 180 degrees. So if you keep those two operations in mind, you will get a much, much more glorious Cayley diagram. And you can check online or check the notes to find out what it looks like. And right, there is also this octahedron, or 8-sided die, if you're familiar with all sorts of RPG games and such. And these two are actually dual to each other, because if you just take the center of the face of this one, you get this one. And you can do the same. So this must have the same symmetry. And the symmetry of these two are called S4, which we're already going up to 24 elements. And then there's another set, Platonic solid. And if you play Magic, you would use the 20-sided dialogue. And there's a 12-sided, which have the same thing. If you take the center point, you get each other. So these two also have the same group, which is A5. Fun fact, if you keep reading Nathan Carter's book to the end, you will realize A5 is curiously related to a very interesting conclusion, is that we cannot solve all the quintic equations. So for up to power 4, we can solve it with a quadratic equation formula and such. But a quintic equation just cannot be solved, and somehow it has to do with the symmetry group of these guys. And there's also this guy. This guy is not a Platonic solid. It's just made for game purpose, I think. All right, so that concludes the first lecture of visual group theory, and tomorrow we'll dig into Lie groups.